Hello, my name is Bhagwat Yedla. My co-participants Praful, Darshit, Girish, and Dr. Sandeep Ray, and I are here to present our topic on AUTOHAL, hands-on exploration of vulnerabilities in automotive systems. So vehicular systems have seen a rapid transformation in recent years with an explosive infusion of autonomous features. And modern automobiles include hundreds of ECUs or electronic control units, each attached to a variety of sensors and actuators, several in-vehicle networks, interfaces, and wireless protocols for communicating with several external entities and hundreds uh, of megabytes of software. So an upshot of autonomy has increased the susceptibility of these systems to cyber attacks. And recent research has shown that it is surprisingly easy for a malicious entry to subvert a vehicular system, causing catastrophic accidents and possibly bringing down the transportation infrastructure. Awareness of the role of security in vehicular systems remains limited in the cybersecurity community. Unsurprisingly, in recent survey by the world's second largest reinsurer, Munich Re, 55% of the surveyed corporate risk managers named vehicular security as their top concern for autonomous vehicles. Yan et al. Showed how to compromise sensors in actual vehicles through jamming and spoofing. Lim et al. Demonstrated an attack that jeopardizes the accuracy of ultrasonic sensors, leading to object detection failures. As far as other sensors go, Petit et al. Showed jamming, spoofing, blinding, and replayed attacks remotely on LiDAR and camera-based systems using mere commodity hardware. So we address this problem by developing an exploration platform that enables users with limited domain knowledge or expertise to get a sense of security challenges in modern vehicles. And we name it AUTOHAL. AUTOHAL enables the user to play with a variety of automotive security compromises. The focus of this project is on ranging sensors that are used by autonomous vehicles to develop an internal perception model of its environment. An adversary providing wrong or misleading sensor values to the vehicle can coerce it into unsafe or insufficient driving maneuvers, example by distorting the distance of a vehicle from a pedestrian or any obstacle for that matter, ultimately leading to accidents. So we discussed some of the interesting research challenges in developing such an exploration platform and our approaches to address them. So in spite of significant literature on sensor attacks, we have not found a platform that can be used as a hands-on exploration platform to learn how to conduct such attacks. Note that developing a useful pedagogical experimental platform that lets a new user to get an overall sense of the attack and its impact is different from a demonstration of an attack by an expert. Obviously, unlike many real attacks, it is not possible for someone to use actual vehicles. Apart from being economically infeasible, it is ineffective for learning. So also the platform must include or provide control guidance to the user. A sensor attack involves tweaking multiple sensors and parameters in particular. The platform must allow the user to tweak a broad and sometimes unanticipated range of parameter values, even though that does not result in any security compromise. Finally, the platform must provide configurability and extensibility so that the platform is reusable for a variety of attacks. The hardware implementation consists of two modules, an attack equipment and a victim proxy vehicle. So the attack hardware is equipped with an attack sensor or an array of sensors that transmit signals that blind the sensor on the vehicle or spoof the existence of an object in its vicinity. Victim vehicle proxy runs on a Raspberry Pi and uses an ultrasonic sensor that communicates distances of objects around it. And the AUTOHAL architecture includes a user interface panel that enables the user to tweak the various attack parameters and obtain feedback. Example, observe interference patterns created by programming the sensor's position and the frequency for specific values. The other one is the physical attack environment that comprises of the attacker sensor to perform sensor attacks and the victim vehicle proxy that includes a mobile agent with automotive sensors attached, uh, which is the target of the attack. And the third one is a platform controller that provides the coordination between the user interface and the physical attack environment. There are two attack mechanisms, spoofing and jamming. So a spoofing attack is a type of man-in-the-middle attack. It involves emitting ultrasonic pulses identical to the victim ultrasonic sensor. The spoofing signal for an attacking sensor introduces a false distance. And jamming is a type of denial of service attack that provides an external interference signal capable of overpowering the actual ones. Multiple jamming signals blind the sensor and then produce out of bound distance values. We have included some usage model parameters. We used a HCSR04 sensor and a linear actuator module to blind sensors and spoof non-existent objects around it. Parameters such as trigger rate, height, type, and the number of attacking sensors were given to the user to play with. And the user is notified with feedback messages on the GUI for the parameter values provided as input for an instance of an attack. We have a small demo.
Welcome to the demonstration of AUTOHAL. Firstly, we'll begin with a benign scenario wherein a car is stopping at a certain distance from an obstacle ahead. Let's look into the GUI for our attacking platform. There are 4 parameters which can be varied, that is, the type of sensor, height of an attacking sensor, trigger frequency, and number of attacking sensors being used. We also have a feedback message section with 2 buttons, start and stop of an attack. This is the benign scenario where this car is stopping at a certain distance, yellow marker. Now we'll move into spoofing attack. Certain parameters like the trigger frequency, height of the attacking sensor have been varied, and the same feedback message is obtained saying that it is a low quality attack being performed. And you can see once you click on the start attack button, the ultrasonic sensors in the attacking platform comes up and starts attacking. The car is being held at a farther distance from the actual stop distance due to the false distances recorded inside the car. This is a spoofing attack wherein it is made to believe there is an obstacle ahead even though if it's not there. Jamming attack. Jamming attacks are performed again with varying some parameters like having a better trigger frequency and the better height calculations. Jamming attacks. Jamming attacks have been performed again with varying parameters from the GUI. The trigger frequency have been put to the best possible frequency, and as you can see, a good spoofing or a jamming attack can be performed using such a trigger frequency. The same can be seen in the demonstration. The car comes to halt at a yellow marker, that is the benign scenario. Once it's at a halt stage, the attacking platform starts attacking the car and make it believe that there is no obstacle ahead. This makes the car go ahead and collide with a sensor or the obstacle ahead. This is jamming attack. Thank you.
Ranging sensor attacks are used by vehicles to detect a variety of features in their environment. We conclude by stating that AUTOHAL enables the user to explore and comprehend attacks on ranging sensors, including spoofing, and extend it to jamming attacks. AUTOHAL can be used for teaching automotive security to students new to automotive systems and also train industry professionals with automotive systems functionality who have got knowledge of or familiarity with automotive systems functionality but unfamiliar with security. In the future, we plan to extend AUTOHAL to handle sophisticated sensor attacks. We would like to extend the platform to incorporate automotive grade sensors. We want to include AR VR platforms for an immersive learning experience. That's all we have for today, and thank you.